Hi folks, welcome to the Math 621B Chapter 8 Concept Roundup. In this video we'll be looking at logarithms, and you can see the topics that are listed here. As always, there's a link to the downloadable notes in the video description below, as well as a link to a review that you can do on your own. The video is also time-stamped down below, so if there's some topic that you see here that you want to jump to, just look for the time at which it starts. As always, this is not an exhaustive look at Chapter 8, but these are kind of the key concepts. So let's dive in and define a logarithm. Here's how I like to think of it. If I see log base 2 of 8, that's asking me a question. And here's the question it's asking. To what power do you raise 2 in order to make 8? Or alternately, you could do this kind of graphically. You could say, when I see log base 2 of 8, it's thinking. This is our daydreamy mode. 2 to the power of what gives me 8? Oh, we can think that through pretty easily. 2 to the power of 3 gives you 8. So the value of log base 2 of 8 is 3. It's the missing exponent. That means whenever we have an exponential statement, we can convert it to a corresponding log statement. So let's take a look at what we're well familiar with, the exponential form. Something like this, 2 to the power of 3 equals 8. Okay, and this has certain features. It has a 2, which we call a base. It has the 3, which is the exponent or power. And it has this 8, which we could call, I don't know, the answer or the result. Now we know that in log form, it looks like what's right up here. Okay, log base 2 of 8 equals 3. Still a true statement. Now take a look at where each of those features of the exponential form ended up in logarithmic form. The base went over here to become the base of the new logarithm. The exponent, that became the equals part. Okay, what goes on the other side, or the answer to log base 2 of 8. And what was the answer or result from exponential form? That is the thing we're taking the log of. So these are both true statements. They're just written in different forms. They both mean the exact same thing. And when we put it in logarithmic form, sometimes the way you can remember it is that it goes base and then answer from the exponential form. And on the other side, you have the exponent. So when you're dealing with log, you have bay. OK, let's look at a few other features. In a log expression with a base of c, if we're taking log base c of a and c need to be positive. And that's because you can never raise something to a power and make it negative. You can't take a positive number, raise it to a power, and make it negative. So that's why a needs to be positive. And the c needs to be positive because basically exponents are really poorly behaved if we have a negative base. If no base is shown, the base is assumed to be 10. So if we had started off, instead of having log base 2 of 8, if we had just seen log of 8, there would be an assumed base there of 10. OK, the next three, let's think about these. Log base c of 1. So go to daydreamy mode. That's asking you a question. It says c to the power of what is 1. Well, what power do you need to raise something to in order to make a 1? You need to raise it to the power of 0. So log of 1 is always going to be 0. The next one, let's think of that in daydreamy mode. It says c to the power of what gives you c? Obviously, c to the power of 1 gives you c. So if the base and the thing you're taking the log of are the same, you'll have a 1. And the last one is just a definition. If we take c and raise it to the power of log base c of m, those are essentially opposite operations. So we end up with just the m. And that's assuming that m is greater than 0 and that you could actually have taken the log in the first place. Okay, so we want to be able to switch forms here. Let's practice that. Switch between logarithmic and exponential forms. We have 3 to the negative 2 equals 1/9. So right here, the base is 3. So when we go to log form, we want base first. Base, answer, exponent. The base would be 3. The answer from exponential form would be 1/9. And the exponent would be negative 2. And that's saying the same thing. It's saying 3 to the power of negative 2 is 1/9. Okay, same thing with the next one. Right here, it's given in log form. So it's given as bay. So the base is 25. The exponent is a half. And the answer or result would be a 5. Now let's see, is that true? 25 to the power of a half? Is that 5? Absolutely. 25 to the half is a square root of 25, which is the number 5. Let's actually evaluate some logarithms here. So we have log base 2 of 16. So what is that saying? That's saying 2 to the power of what is 16? Oh, 2 to the power of 4 is 16. So the log base 2 of 16 is 4. Okay? And that's the answer, is the 4. Don't write 2 to the 4 as your answer. That's a different number from 4. Boo. The answer is the missing exponent. Let's try another one. Log base 5 of 1 over 25. In daydreamy mode, that's 5 to the power of what gives me 1 over 25. Now, how do you turn a 5 into a 1 over 25? Well, you need to flip it, which means a negative exponent. And then you need to square it to turn a 5 into a 25. So the missing exponent here would be a negative 2. Okay? So that would be the answer, is negative 2. When we deal with logarithmic equations, which we'll do more later on in the video, often we end up switching between logarithmic and exponential form. So down here I have something that's in logarithmic form. I'm not quite sure exactly what it means, but I know it's base, answer, exponent. So let me write it in its other form and see if that helps. It would be 9 to the power of negative 1/2 equals x. Okay? That means taking 9 and flipping it upside down and square rooting it, where x is equal to 1/3. And that's easier to see from exponential form than from logarithmic form. Let's keep trucking here with basic logarithmic graphs. So from chapter 7, here's what we know about the graph of y equals 5 to the x. We know that it basically looks like a banana, that if I put in a 0 for x, I'd get 1 for y. 5 to the 0 is 1. If I put in 1 for x, I'd get 5 for y. 5 to the 1 is 5. And it has an asymptote on the x-axis, and it looks like this. Now let's consider its inverse. Okay, well, first of all, if this one has the point 0, 1, and 1, 5, its inverse is going to contain the point 1, 0, and 5, 1. And it's going to look like this, so that they're reflections of each other through that 45-degree line. Okay, so graphically, that's definitely what the inverse is. In terms of an equation, inverse comes from switching x and y. So we get x equals 5 to the y. And if I got the computer to graph x equals 5 to the y, it would give me that blue graph. We really, really don't like equations in x equals form, though. So we've got a problem. The y is stuck up in the exponent. Let's try switching forms. So if we were to do that, we'd say log with a base of 5. That's the base here. The answer from the exponential would have been the x. And the exponent would have been y, b-a-e. Or write it the other way around. Y equals log base 5 of x. These two things are inverses of each other. Okay, so they're related. They undo each other, logs and exponents. So the big idea here is that exponentials and logarithmics are inverses. Now that we know that, let's try and characterize some of the basic things about logarithmic graphs. So you can just look at them and see, well, that blue one, instead of having a horizontal asymptote, it has a vertical asymptote on the y-axis instead of the x-axis. It does look like it's increasing. So it has this basic shape. Does this. It has no horizontal asymptote. It rises slower and slower, but it's never bounded on top. It does continue upwards and upwards and upwards. Okay, it has a vertical asymptote at the y-axis, which is the line x equals 0. The domain, you could write it as x is greater than 0, or if you prefer, x is an element of positive reals. And that's because you can't take the log of a 0 or a negative number. And that was basically in our first slide. The range, you can see it goes up forever, goes down forever. And the points that are in your basic logarithmic graph are this one, 1, 0, and C1, where C is the base. So let's sketch this one that's down here. Y equals log base 4 of x. It's going to have this basic look. It will go through the point 1, 0. And another point that will be known to us on it is the point C1. Well, C is 4 here. Okay. If that had been log base 5 of x, well, we'd have 5, 1. If it had been log base 23 of x, that would be 23, 1. Okay. So that's what the basic ones look like. But of course, we're not content with just having the basics. We're going to start to transform them just like we did in Chapter 1. So we'll do a real quick recap here on what all the parameters do. If I have y equals log base a log base c of b x minus h all plus k. Here's what we know. A controls your vertical stretch. So vertical stretch by a factor of a. And it can also give you an x-axis reflection. Now, when we did this for exponentials, we got all these descriptions, and we ended up not really needing them because we just went to a table of values. Here, we will need the descriptions, or to be able to analyze. The b is a horizontal stretch, and that's by a factor of 1 over b. If it's negative, you might end up, well, you will end up with a y-axis reflection. All right, the h, that is your horizontal shift. And that's going to end up controlling the vertical asymptote. It'll shift it either to the right or the left, such that the vertical asymptote has an equation of x equals whatever that h value is. Okay, and finally, we've got vertical shift. Now, you might remember your mapping rules, which tells you that the point xy is generally transformed into 1 over b times x, that's the horizontal stretch factor, plus h, that's the horizontal shift, and the y value gets times by the vertical stretch factor, which is a, and then plus k. I often forget, which is silly, but if you do forget, you can always just describe the transformations and make your mapping rule out of that. It ends up being pretty straightforward. So here's the approach we'll take to graphing a transformed log function. We'll describe the transformations. You can do without that. And then we'll make a mapping rule. We'll draw the vertical asymptote because it's the most important feature of the logarithmic graph. And then we'll just map the images of the important points that we saw in the last slide, namely 1, 0, and C1. And I'm just going to do one example here, but it's one with a whole bunch of pieces to it. So it's got a bunch of transformations. I think we'll need some space. So here we go. Y equals negative 3 log of 2x minus 1 plus 5. Okay, let's start cataloging what's happening. A negative here, that's an x-axis reflection. Okay, and it's also got a vertical stretch by a factor of 3. This 2, that's a horizontal stretch by a factor of a half. This means right 1, and that controls the asymptote. So this might be the most important one. And finally, we're moving up 5. Okay, since that right 1 is there now, I'm going to use it and move my asymptote, which is usually on the y-axis, over 1. I know this is going to be important. X equals 1 is that asymptotic line, vertical line. Okay, now we're going to go and make a mapping rule. So, if we had some general point xy, and it had all these things performed on it, let's see what would happen. Horizontal stretch by a factor of a half, that means you take your x value and you multiply it by a half. If you go to the right 1, then that's adding 1 to x. An x-axis reflection, that flips all your y values from positive to negative or vice versa. So it makes your y's negative. And a vertical stretch by 3 means, factor of 3 means your y's get multiplied by 3. So we'd have negative 3y, and then up 5. So our y's would have 5 added to them. Okay. If you use the mapping rule that's just up here, you can see I just took those values and they're plugged in. You can do it either by describing or by just looking at what a, b, c, h, and k are. Okay, next thing we're going to do is we're going to map the important points. So usually on a logarithmic graph, we have 1, 0. Let's see what happens. If I plug in 1, 0 over here, I'll have 1 times a half is a half plus 1, 3 over 2. Negative 3 times 0 plus 5, so I'm putting in 0 for y over here. That's going to give me 5. Okay, so let's plot this point. It's at 3 over 2, or 1.5, 5. The other important point was the point C1. Now, up here, if we take a look at this log expression, it shows no base. So the base is assumed to be 10. That's not a negative 10. That's just the convention. You write a dash. So base is 10. So normally, this would have the point 10, 0. Sorry, 10, 1, rather. Okay, let's see what happens. If I put 10 in for x over here, I'll get a half times 10 is 5 plus 1 makes 6. If I put in 1 for y, I'll get negative 3 plus 5, which is 2. So the point 6, 2 should be on here. 4, 5, 6, 2. And then I just connect them, paying attention to my vertical asymptote. And there is no horizontal asymptote. Yes, it's above the x-axis for now, but eventually it will cross it and go downward. Okay, so there's our basic shape. We transformed the 2 points, and we used the asymptote and that mapping rule. When you get used to doing them, that should take you about 2 minutes. Okay, so you can see that if we looked at those other ones, we'd have restricted domains. The graph back here, obviously it has a domain of x greater than 1. And we want to be able to pull that out without the graph, what the domain restrictions are. So here are the illegal operations in the real number system so far. Division by 0, we already knew about that. Even roots of negatives, we already knew about that. And logs of negatives and 0. So it leads to domain restrictions in functions. If you had something like this, log base c of x, well, let's think about that. You can't take the log of a negative or 0, so x would have to be greater than 0. And often what will happen is students understand that well, but then they'll see something like this, x squared minus x. Okay. Whatever we're taking the log of has to be greater than 0. So the domain's going to be x squared minus x is greater than 0. Now you might want to actually work out those values. I like to generalize as much as I can. So when we say this, we mean x could be anything. So it could be some complicated function of x. It could be a parabola. It could be a cubic. It could be, let's imagine that it's some poorly drawn unicorn. And that's some function of x. Whatever we're taking the log of, even if it's the poorly drawn unicorn, the domain is going to be that thing has to be greater than 0, assuming it has to do with x. Okay, so whatever we're taking the log of needs to be greater than 0 in the domain. So over here we have y equals log base 3 of x minus 3. What's the domain? Whatever we're taking the log of, x minus 3, that has to be greater than 0. Okay, now work it through. X is greater than 3. There's our domain. Over here, we've got a bunch of other stuff. We've got some reflections. We've got a vertical shift of up pi. But it's whatever we're taking the log of has to be greater than 0. And I don't know how to break it down any better than that. Whatever you're taking the log of is greater than 0. Okay, and then we just work it through. That means x is greater than negative 5 over 2. And if we were to generate the graph of this, it would bear that out. And for whatever reason, it doesn't want to generate that graph for us right now. You could grab a graphing calculator, and you'd see that the domain really will be x greater than negative 5 over 2. Okay, and finally, for logarithmic graphs, x-intercepts. As always, x-intercepts in any function are found by substituting 0 for y. So if we have this function over here, y equals negative 3 log x minus 1 plus 6. If I want the x-intercept, I just sub in 0 for y. Now this has a whole bunch of mess to it. You probably want to isolate that logarithmic term, so I'm going to bring my 6 over. I could divide by negative 3. That'll give me 2 equals log x minus 1. You might say, well, that doesn't really help us a lot. But this has another form. Remember that the base of this log is 10 because no base was shown. So if I write this in exponential form, here's how it looks. 10 to the power of 2 equals x minus 1. And if we solve that, we'd have x equals 100 plus 1, or 101. Our x-intercept is at 101, 0. Okay, the number e. Not in your book, but it's important for us to have a quick little glance at this because it's going to come up more and more. The number e is an irrational number, like pi. It's often used in exponential and log functions. Its actual definition is this. It's the limit as n gets infinitely large of this expression. So if I put in bigger and bigger n values, if I put in 1,000,000 or 1,000,000,000, this gets closer and closer to a value that is roughly 2.72, but isn't exactly 2.72, just like pi isn't exactly 3.14. It goes on forever. It has no pattern in its decimals, and its decimals never stop. Okay, so that's the number e. It has special properties that will be useful in calculus. For now, we're just sort of getting acquainted with it, and we're saying that if you were to look at your calculator has a log button right here. Okay, log. There's also another one. On mine, it's just below that says ln. And ln means a log with a base of e. It's the other common base for exponentials and for logarithms. So up here we say, for now, let us define a log with a base of e as a natural logarithm. It's abbreviated ln and pronounced ln. So here is the definition over here. Ln a means log with a base of e of a. Ln 1 would be asking you a question. It would say, e to the power of what gives you 1? Well, anything to the power of 0 gives you 1. So ln 1 is 0. You don't want to go around shouting, I'm number ln 1, because that's no good. That means you're number 0. Boo. Okay, the next one. Ln e means e to the power of what? Gives you e. Okay, because ln is just a log with a base of e. The answer here would be 1. And e and ln are opposite operations, so e to the ln m is going to be equal to m. The graphs are the same as all other exponential and logarithmics. So here if I put in 0 for x in this, then I'd get 1. So that's a point on the graph. If I put 1 in for x, I'd get e, which is 2.72-ish. So this would contain the point 1e. And like all other exponentials, it would have a horizontal asymptote. If I wanted to graph y equals ln x, which again means the same thing as a log with a base of e of x, it would have our standard properties. It would look like this. It would have the point 1, 0. And the other point that it would have would be the base, which is e, 1. Okay, so this would be the point e1. And you can see just by looking at those two, they're obviously inverses of each other. The points are just flipped with x and y. So nothing becomes any more difficult when we're dealing with logs with a base of e. They just happen to exist, and they're going to be helpful for us later on. Okay, log laws. 3 basic laws that we use here. Log base c of m to the power of p. It's probably the most useful of the laws. This p, it can be popped down front. And we're not going to go into the proof in this video here. You can find that somewhere else on the internet. This is just a little review so that you know you can do that. Okay, there's also a product law, and it says that when you add 2 logs of the same base, what you can get is a single log expression of those 2 things multiplied together. So when you put them together, you multiply what you're taking the log of. Similarly, there's this quotient law, and it says when you subtract logs of the same base, we divide to combine them. So this would be m over n. The one that's being subtracted always ends up on the bottom. Let's evaluate. Log base 12 of 2 plus log base 12 of 6. We can put those together as log base 12 of 2 times 6, or 12. Okay, so again, that's asking us a question. It's saying, now, 12 to the power of what is 12? Oh, the answer to that is just 1. Okay. So if you go to the store and you order log base 12 of 2 plus log base 12 of 6 donuts, you should get 1 donut. Okay. And it's interesting that we can find that value of 1 even though we don't really know what the log base 12 of 2 is. Let's try another. 2 log base 6 of 2 plus log base 6 of 9. We can't put these together because of this pesky 2 out front. We don't have just log plus log. But that 2 could have been an exponent that lived on top of the 2. That's the power law, kind of in reverse. So I could rewrite this as log base 6 of 2 to the power of 2 plus log base 6 of 9, or log base 6 of 4 plus log base 6 of 9. Now I'm ready to use that product law. I can put them together in a single log. I'll just have the log of 4 times 9, which is 36. So log base 6 of 36. And that's asking this question. 6 to the power of what gives me 36? Oh, 2. So that whole expression we started with just means the number 2. Let's do one more. 1/2 log base 17 of 4. I have no idea what the log base 17 of 4 is. But I know that this could live up top. So I could call this log base 17 of 4 to the half minus log base 17 of 2. Now 4 to the half is the same as square root of 4. So we get log base 17 of 2 minus log base 17 of 2. What do you suppose that's going to be? Anything minus itself is just going to be 0. Let's see if the quotient rule also shows that. So this would be log base 17 of that 2 divided by 2. Or log base 17 of 1. Which is asking this question. I'll just put it up here. 17 to the power of what gives me 1? And the answer to that is 0. Okay, so that makes sense. It looked in an earlier step like the answer should be 0. And it still means the same thing if we use the log laws. So sometimes we'll want to use log laws to combine. And sometimes it will be more convenient for us to use them to split apart. Now here I sneaked in a ln, but ln just means a log with a base of e. So all the log laws apply. Ln is a log, just happens to have a base of e. So we've got division here. That means we can use the quotient law. We can split it apart as ln of a squared minus ln of b root c. Okay? Because we want to express it in terms of ln a, ln b, and ln c. Well, that's a start. Now that first one, the 2 could pop down front from power law, 2 ln a. Over here, I have ln b times root c. So those could be split apart using product law. Those are two things that are multiplied together. But the whole thing's being subtracted because of this subtraction sign out here. Okay, that's important. That's why we have these brackets. Okay, things are starting to look up for us. We're getting a little closer, so that gives me 2 ln a minus ln b. This will now be minus ln root c. So close. We've got ln a, ln b. We have ln root c instead of ln c. Let's see, how else could I say that? Square root of c is c to the half. Ooh, if we think of it exponentially, then we can use that power law again. So we're just getting creative about how we can get this down to only ln a, b, and c. And there are times when it's going to be easier for us to have things written in this form. The simplest thing possible within the logarithmic expression. Okay, we're almost at the end here. We have two kind of big topics, and in your book these are 8.4. One of them's on exponential equations, and the other one's on logarithmic equations. So when we did chapter 7, we were able to find a technique for solving something like this. 2 to the x equals 8. We could solve because a common base was possible. 8 could be 2 to the 3. But if we changed it just even a little bit and we had 2 to the x equals 7, we would be totally out of luck, which is kind of frustrating. Well, now that we have logarithms, we have an approach for solving that type of equation. And here is the approach. Number 1, isolate the exponential term if it's possible. Number 2, take the log of both sides, either a natural or base 10 log, it doesn't matter. If you see an e, you should probably use a natural log. Use log laws and rearrangement to solve. Okay, and I'm not going to do the absolute toughest ones here. We just want to get the point across. So I'll do 3 examples. So this is the basics right here. 2 to the x equals 7. I can do anything to an equation as long as I do the same thing to both sides. Isolate the exponential term. Done. 2 to the x is on its own. Take the log of both sides. I'll take log base 10 because I feel like it. I could have just as easily taken log base e. Okay, but it has to be one that your calculator does. So we have log of 2 to the x equals log 7. Now here's the special feature. This x can now pop down front. So we can have x log 2 equals log 7. Now to get x on its own, we just divide by log 2. Okay, and you can't just divide by log. That would be like dividing by plus. It doesn't make sense. It's something that does something to a number or a variable. So the log 2's are gone on the left. And on the right we have log 7 over log 2, which is unhelpful unless we get our calculator to give us a hand. So log 7 divided by log 2 gives us 2.81 as an answer. And we can also show that if you had chosen instead to use ln, so log base e, we would have ended up at the same spot, but with lns, I wonder if it'll give us the same answer. You betcha. So either way is good. Now let's see if it's true. Is 2 to the power of 2.81 7? Yes, it is, with a tiny rounding error, and that's because I rounded my final answer to 3 sig figs. Okay, let's try another one. 5 to the x plus 1 equals 3. So again, our exponential term is isolated, so I'm just going to take the log of both sides. It means that I can pull that exponent down, and I'm pulling it down all together, so it goes in brackets. At this point, since we're looking to get x on its own, I'd be inclined to divide by log 5. You could distribute out if you prefer. And that means on the left side we've got x plus 1. On the right side, we've got log 3 over log 5. Let's figure out what that is, and we'll keep some extra significant figures. I usually like to have my final answer correct at 3 sig figs, so I'll keep more as I go along. Maybe I'll do 4 for now, and then round at the end. 0.6826. Looks good. Okay, and that's what x plus 1 is equal to. If I want x on its own, I'm just going to subtract 1. So negative 0.317. Okay, and if you go and check that in the original equation, it really will work. Let's do one more. So the first step had been isolate the exponential equation here, or exponential expression. Here there are 2 exponential expressions. You can't isolate them, so we'll just move on to step 2, which is take the log of both sides. 5 to the x plus 1 equals log 3 to the 2x. Okay, I can pull my exponents down. This is the great gift of the power law of logarithms. Okay, now it might seem like getting x on its own is tricky. So if you have multiple x's, here's what you should do. You should distribute out and see what you get. So we'll have x log 5 plus log 5 equals 2x log 3. You should collect all your x-type terms on one side. So I might as well move my x's to the right since it only has x's at this point. So I'm going to subtract x log 5 from both sides. And here's what I'll have. I'll just have log 5, or ln 5 if you preferred to do this all with natural logarithms, equals 2x log 3 minus x log 5. Still doesn't seem that helpful. But both the terms on the right have a common factor. They have a factor of x, and you want to pull that out. So we'll have x bracket 2 log 3 minus log 5. This is what's going to help us isolate x. And now you can see that if you want x on its own, I just divide both sides by this, by 2 log 3 minus log 5. And I'm putting it in brackets because I'm thinking about my calculator here, that it might not have this big division symbol. I might have to put it in just as a regular division. And I wanted to know to group those green things together. So x is going to be log 5, close bracket, divided by open bracket, 2 log 3 minus log 5, close, close. And I get 2.74. Okay. Notice everything on the right-hand side would have divided out. These would be gone, and you're left with just x. So that's the basic technique for exponential equations. You might run into a few hiccups in more challenging ones, but that's how we deal with having x's on both sides, and how we deal with having, say, a binomial in the exponent. Okay, lastly, logarithmic equations. There are, as I see it, two types, just like there's two types of factoring for trinomials, a short and a long. And they're easy to tell apart. Short logarithmic equations have a single log. And the idea is that you isolate the log term, you convert to exponential form, and then you should check. And when we check, usually what we're just looking out for is illegal stuff, which means taking the logs of negative and 0. Okay, so as long as that's not happening, typically the numbers will work out fine. So you want to keep your eye out, make sure that the answer that you found doesn't cause you to do one of those illegal things in the original steps. The long ones have many logs, and exclusively logs. And the idea is to create a single log on each side using log laws. Then you'll drop your logs, you get rid of them, and solve. And finally, you check again in the original form. So there's short and there's long. Now you might consider that there's a medium as well. If a log equation contains both log terms, multiple log terms, and regular numbers, it can be converted to either short or long. I like to make those short. It's up to you. Doesn't matter. Okay, so let's take a look at these couple that are given down here. 2 plus log base 3 of x equals 5. Is it short or is it long? It's at like the atomic level of explanation here. There is only one log. It must be a short one. So let's go through the steps. Isolate the log term. That would mean moving that 2 over. So we'd have log base 3 of x equals 3. Awesome. Now let's convert to exponential form. So this is in Bay. So in exponential form we'd have base of 3, an exponent of 3, and an answer of x, or x is 27. Let's check out what happens here. If we check in the original, the left side would be 2 plus log base 3 of 27 equals the right side, which is 5. Right away, we can see there's no illegal stuff. You are allowed to take the log of 27. But let's follow it through anyways. Log base 3 of 27 is the number 3. Hey, we get 5 equals 5. It's a great solution. Let's try the next one. Log base x of 4 equals 1/3. Okay, so the steps for a short were isolate the log term, done. Convert to exponential form, don't mind if I do. The base is x, the exponent is 1/3, the answer is 4. Oh geez, we've got an x to the 1/3. How can I turn that into a regular x? I can cube it. And if we cube both sides, we'll get x equals 4 cubed, which is 64. If we go and check, the left side would read log base 64 of 4. And the right side would be 1/3. Right away, we can see there's nothing illegal happening here. You're allowed to have a base of 64. It's having a base that's negative that's trouble. So this is going to be fine, and if you thought it through, yes, log base 64 of 4 is 1/3. So this is a great solution. Next, we're going to do the absolute simplest example of a long log equation. So if I have this log, and this is base 10 is assumed, of x plus 3 equals log 7. Let's go back here. There are many logs. This is a long one. We want to create a single log on each side. Wow, it's already done for us. There's a single log on each side. Next step. Drop the logs and solve. Okay. So the idea is that if log of x plus 3 equals the log of 7, then it must be that x plus 3 equals 7, or x equals 4. Now let's go check what that does. On the left side, and we're checking in the original, the left side would say log of 4 plus 3. The right side would say log of 7. The left and right sides would say the same thing. Yay, this really is a solution. Okay. But the thing we watched out for here is plugging it in. Did that cause us to do anything illegal? No, you're allowed to take the log of 7. It's a positive number. Now let's take a look at a logarithmic equation that's long but is a little more involved. So here we have an equation that's made up exclusively of log terms, but there are many of them. There are several of them. Our first step, as outlined over here, was to create a single log on each side. Okay, so the right side's great. It's log 4. The left side, we have log plus log. To put those together, we would use the product law, which would tell us that we'd multiply our terms when we put them into a single log. In other words, we'd have log of x squared plus 3x equals log of 4. Great. At this point, we've got a single log on each side, and if they're equal, if their logs are equal, then x squared plus 3x must equal 4. Okay, it's a quadratic. We know how to deal with these. We make one side 0. We factor. And we get solutions of x equals negative 4 and x equals 1. We should just consider these as candidates for solutions at this point, because we absolutely need to check them. So let's check x equals negative 4. The left side would start off like this. Log of negative 4. You don't need to go any further in your check. Log of negative 4? That's illegal. You can't do that. Negative 4 is not a solution, which does not guarantee that 1 is a solution. We also have to check whether 1 is a solution. So check x equals 1. The left side would be log of 1 plus log of 4. and the right side would be log of 4. Now you can verify that that's actually true, but the main thing here is that nothing illegal happened. You're allowed to take the log of 1, you're allowed to take the log of 4. They're not negative numbers or 0. So this is going to work out. So that is a solution. X equals 1 is the only solution. There were 2 potential candidates, but the negative 4 was no good. And sometimes those are called extraneous roots, ones that we found that looked like they might work, but actually don't in the original form. We'll try a couple more logarithmic equations with a few special cases. So right over here, we've got 2 log expressions. It looks like we could just drop the logs, but there's that pesky 2 out front. So I wouldn't know what to do with that when I drop the logs. It's not like I'm taking log away from both sides. There's that 2 as well. What we should do with the initial 2 is put it into the expression. And we know that the power law says exponents can come down front, but we could also use it kind of in reverse and say, well, that 2 could go live on top of the binomial, which would give us this. Log of x plus 2 all squared equals the log of 16. Now we have a single term on each side. Now we can drop our logs. Okay, that gives us x squared plus 4x plus 4 equals 16. Factor it. We get x plus 6, x minus 2. So potential solutions of x equals negative 6 and x equals 2. You might be tempted to say, well, the negative 1 is never going to work. That's not actually true. You might have something set up where the negative 1 works and the positive doesn't. You might have something set up where neither of them work. You need to check them individually. So let's check this one in its original form. We'll check x equals negative 6. Okay. So the left side would be 2 log of negative 6 plus 2. That's negative 4. Oh no, we can't do that. This is right out. Okay, let's check x equals 2. The left side would look like this. 2 log of 4. The right side would be the log of 16. You can take your time, go through, verify that that's going to be true. But right here we can see there's nothing illegal happening, so this is going to be a solution. Just for fun, I'll finish up the check. So that 2 could have lived up top. It would have been log of 4 squared, or log of 16. Hey, the left side equals the right side. X equals 2 must be good. Now, for one last one. We've got log base 2 of x plus 4 plus log base 2 of x plus 2 equals 3. Our technique for long logarithmic equations is not going to be great here because we don't have a log to drop on one side. So what I'm suggesting that you do if you have multiple logs and then a regular number is to sort of do halfway in between the techniques. You're going to try and consolidate your logs as much as possible. So I can use log laws to multiply and put that left side together. Okay? And once I do that, something amazing happens. Well, not that amazing, but once I do that, that is now a short log equation. Okay, it has a single log in it. And the way you deal with short log equations is you convert them to exponential form. B, A, E. Base is 2. Exponent is 3. The result is x squared plus 6x plus 8. And now we just follow it through. Okay, we've got to factor this. Clearly there's a common factor of x. So we have potential solutions of 0 and -6. Now, neither of those are numbers you can take the log of. But that's not really what we're being asked. We're being asked, do they work in the original form of the equation? Let's check them out. Let's check x equals 0. It gives us log base 2 of 4 plus log base 2 of 2. On the right side, it would give us the number 3. Those are all okay things to do. You can take the log of 4, you can take the log of 2. This one is great. We could follow it through. Log base 2 of 4 is 2. Log base 2 of 2 is 1. Yay. But really, right at this stage, we know that everything's going to be okay. All right, let's try the other one. If we check x equals -6, the left side will look like this. Log base 2 of -2. Boo, you can't do that. So that's an extraneous root. And you need to be really, really clear on your tests what you're including in your solution and what you are not. Okay, so I'm really clearly Xing out one and circling the other. I hope that you found this helpful. Once again, there is a downloadable copy of the notes below, as well as a review that you can do. Take care and good luck with your assignments.